Hello. In this video, we're going to continue with our CAD simulations on LTspice. So for this video, we're going to go over the characterization of Vout versus RL. So what that means is we're going to change the load resistor and we're going to see how it affects the output voltage. We're going to do that using the step parameter directive. After we do that, we're going to take a look at the maximum output swing, and we'll achieve that by increasing the input voltage to see what our max output swing is. So I'm going to pull up my schematic, and we're going to start with the Vout versus RL. So pull up the spice directive, type in .step param, press enter, and then right click on that directive. So name of parameter to sweep. What we want to do is change the load resistor. So I'm going to name it RL. The nature of the sweep, we will stick with linear. The start value, I'm going to start with 100 ohms. And the stop value, I want to stop at 10 kilo ohms. And then the increment, I want it to increment by 100 ohms each step. So what this is going to do is it's going to start by having 100 ohms here. On the graph, we're going to see the output voltage with that respective load. And then the next sample, it's going to be 200, right? Because we have 100 as a starting, and it increments by 100. So that means the next load value will be 200 ohms, and we'll see what the output voltage is for 200 ohms. And it'll do that until we get to 100K, 100 kilo ohms. Okay, so we'll press OK. And we named the value RL. So what we need to do is, instead of 2.7K ohms, we need to right click here and name it RL inside of curly brackets, just like this, and press OK. And then we need to do a transient analysis. So you can come up to simulate and type in edit simulation and pull up a transient analysis. And I'm going to have it stop at 104 milliseconds, and we will start at 100 milliseconds. And so I'm doing that to let the circuit settle, and then we will run and then we will measure the output. And so what we see here is this blue line is the output voltage when there's 100 ohm load. And then since we're incrementing by 100 ohms, this red line is 200 ohms. And then you can kind of see the green line is 300 ohms, and then all of the rest of the samples are kind of clustered here. So now that we have this like general idea, we know that we're going to want to look between 200 and past 300. So I'm going to change the directive. I'm going to change it to look between 200 and let's say 500. And instead of incrementing it by 100 ohms, because that'll only give us 3 samples, I'm going to decrease that to 50 ohms to give us at least 6 samples. Then press OK, and then rerun it. And then so now what we have is this first blue line is 200 ohms. This red line is 250 ohms. And then the green line is 300 ohms. And so For this circuit, I would say for the simulation that the lowest load resistance that this circuit can handle is 300 ohms. And I wouldn't say it's 250 ohms because we're getting linear distortion here. And I definitely wouldn't say it's 200 ohms because we're getting clipping. And so what you would want to do for your lab presentation is take a screenshot of this and just observe for your report. And then to go into a little bit more detail about what's going on is first I look at my last stage. So my third stage is a common collector. I'm going to pull up my theoretical calculations. Now granted, my theoretical calculations are going to be a little different than the simulated results, but it'll give you a general idea of what's happening. So looking at my calculations, we have the load resistor is here, and I'm looking at the AC analysis. So R prime E is dependent on the collector current. So that shouldn't change with RL changing. But R little re, which is big RE in parallel with RL, and going back to the circuit, that is, this is big RE and the load resistance. So the resistance of the emitter, the resistance of the load. And I personally call that little re. So it's just something I do to give it a new variable. So that's dependent on RL. And if you look at gain, gain is little re over little re plus R prime E. So when little re is a very large number, this gets much closer to 1. And then as little re decreases, R prime E is able to attenuate the gain a little bit better. Like it attenuates it more, which is going to make our output voltage decrease. So just to kind of quickly show you how that looks, I'm going to increase this to 10K. And then we get closer to a gain of 1, right? If I increased it to 100K, it would go up a little bit. Not by much, but it does. So originally I had 2.7K, and our gain is at 0.995. So if I decrease this to 1K on the load, our gain went down. It's 0.9919 or 0.992. Okay, so then let's just cut that in half again just to see how the circuit is acting. So now it's 0.987, right, with a load of 500. So with a load of 400, it decreases a little more. Then a load of 300, it decreases even more. But our output voltage is still 2.18, where originally for the theoretical it was 2.21. So then we can just keep decreasing this. And now we see it dropped by 0.02 volts. So as the load resistance decreases, our gain is going to be attenuated. And so that is the characterization of Vout versus RL. And you just want to take a screenshot of your results using the step parameter and observe how decreasing the load resistance is going to attenuate the voltage on the output. So moving on, we're going to take a look at the max peak-to-peak value. or the max output swing. So I'm going to erase the step parameter. I'm going to keep the transient analysis, but I will put this back to my load resistor of 2.7K. Okay, so what we have is I'm sending an input of 20 millivolts peak to peak, and I'm getting about 2.29 volts on the output. So if I go to my calculations again, you should have a calculation for each stage for the max peak to peak. And so what you do is these are your formulas for max peak to peak, and then it'll give you two results. And your max peak to peak value is going to be the less of the two. So 6.489 volts peak to peak would be my max peak to peak value of the first stage. So then I go and look at the max peak to peak value of the second stage. And so the max peak to peak value of the second stage is the lesser of the two, so 6.9 volts peak to peak. And I go to the last stage. I'm looking at the max peak to peak values at the last stage, and I'm getting a 10.65 volts peak to peak out of the lesser of the two. So looking at all of the max peak to peak values, the lowest one is this 6.48 volts peak to peak. So that will be my max peak to peak of the entire circuit. And so to be able to see the max peak to peak value, what you're going to do is you're going to slowly increase the amplitude. We see by increasing the amplitude, I'm at 4.47 volts peak to peak. It still looks like a sine wave, so let's increase it a little bit more. Let's do 0.22. And it increased, the voltage increased, and it still looks like a sinusoid. So now we'll increase it a little bit more. So here's a max peak to peak. The output voltage is 6.17 volts peak to peak, and you can see that it's starting to have some linear distortion, right? So like this hump on the top portion of the sinusoid is round, and then on the bottom portion it's starting to stretch out and become more sharp. So just be aware of that distortion that's occurring. So I'm going to increase it a little more. I'm getting 6.34 volts peak to peak. So now let's just increase it a whole bunch and see what happens. So now we increase it up to 0.6, run it, and now it's clipping. Okay? So this is not necessarily our max peak to peak value, because we're hard clipping. What you want is the output to be as close to a sinusoid without clipping. So here we can see a little bit of soft clipping on the top. Our output is 7.62 volts. So I'm going to decrease it a little more. Still, we have a little bit of soft clipping on the top. It's getting a little better, you know, and so we just decrease it a little bit more. It's kind of a touch and go, like going back and forth and playing with it. So I would say there's a tiny bit of linear distortion, but this is probably the maximum output you're going to get before it starts clipping. So increasing the input signal to get an output signal that is not clipping. So our max output swing would be 6.49 volts peak to peak. And this kind of, it takes a little bit of interpretation for you. It's a little bit up to you. Like, the input voltage that you go with might not be 0.031 volts. It might be, you might go with 0.03 or 0.032. And that is completely fine, but you're trying to find that point where you're starting to get a little bit of linear distortion, but it's still a sinusoid. It's not hard clipping, because if you hard clip, your max output peak to peak is much larger than your theoretical. So you're trying to really hone it into a good sinusoid. Like this, you could see it's a little tiny bit of linear distortion, but it's still a sinusoid. And so that's kind of why I went with 0.031 volts. It's not really clipping, but we're getting some linear distortion. And that is your max peak to peak. So you would take a screenshot of this and include it in your lab report under the simulation section. And just to kind of go back over some of the calculations, your max peak to peak is the lesser value of the two. So there's two different equations, and your max peak to peak will be the lesser value of the two. And then this optimizing Q point, which I included in the first video of this series, will help you maximize your peak to peak. So if you're having issues having your circuit in saturation or in cutoff mode, like say right here, if your max peak to peak looked like this, right? So one equation is 4.78, and then the other equation is 15.4 volts peak to peak. These two numbers should be pretty close together. So if you're looking at your optimizing Q point equation, we know that the optimized Q point, to get the quiescent point in the middle of the load line, the whole emitter resistance should be 690. So then you would decrease these to get pretty close to 690. And just to go back, you could see that what I used for mine was actually 700. And so I came up with about 6.5 and 7. But if I did do 690, these two get even closer. So there was a little bit more wiggle room I could have gotten out of my max peak to peak. But 260 ohm resistor value is kind of uncommon, and so I stuck with 270 because that is actually a resistor value that's more common. So I hope this helps for your simulations, and we went over the Vout versus RL, and we went over the max peak to peak values. And again, I would definitely save these in like Notepad or in a Word document, because you'll use them a lot, and it's easy to just be able to refer to this and copy and paste rather than trying to memorize it. Thank you.